moving on to example 7, we're going to show that a matrix has no inverse. So find the inverse of the matrix if it has one, or state the inverse does not exist. So here's what we're going to do here. It's really not a hard concept, just a little bit different. So what we're going to do, we're actually going to add a matrix of x, y, z, w, and again, by our definition, that will equal 1, 0, 0, 1. So now we're going to come up with some equations. So when you multiply these two matrices here, we're going to have 6x plus 3z, and that will equal 1. That's our top left. And then we're going to have 6y plus 3w equals 0. Then we're also going to have 2x plus z equals 0, which will come in very handy in just a moment. Then we'll have 2y plus w equals 1. So we can do this a couple different ways. Well, if I multiply my bottom equation here by 3, that will give me 6x plus 3z equals 0. Here's our issue. 6x plus 3z cannot equal 1 and 0 at the same time, so there is no inverse. There you have it. You showed that there is no inverse. Now, another way you can do this is by finding the determinant of the matrix. Now, if I need to find the determinant of this matrix, I'm going to enter my matrix. This will be a 2 by 2 matrix. It'll be 6, 3, 2, 1. Now, one thing that we're actually going to talk about in the next example, we're going to find the determinant of this matrix using our calculator. And you'll see the determinant of this matrix is 0. If the determinant of a matrix is 0, it will have no inverse. Now, example 7b, we have 1, 2, negative 1, 2, negative 1, 3, and 3, 1, 2. Now, I do realize it's not on the smartboard lesson here, but we can still put it in. So enter the matrix. It is a 3 by 3 matrix. So you have 1, 2, negative 1, 2, negative 1, and 3, 3, 1, and 2. Now again, if I have to find I'll find the determinant of the matrix. And again, because the determinant of the matrix is 0, therefore there is no inverse. Now I realize we haven't really talked about determinants yet. That's what we're going to talk about here. So the determinant of a square matrix. Now there's a simple test that determines if a 2 by 2 matrix has an inverse. And again, we've already gone over this. If the determinant of the 2 by 2 matrix is 0, then there is no inverse. If it is not 0, then we can find an inverse using the formula here. 1 over the determinant, that's how you find the determinant, times the matrix D, negative B, should be negative C, A. This should be a negative C here. Now the number AD minus BC is the determinant of the 2 by 2 matrix. To define the determinant of a higher order square matrix, we need to introduce the minors and cofactors associated with the entries of the square matrix. The minor corresponds, it's going to be a shorter 2 by 2 matrix. So really what we're going to do here, when we find the determinant of any square matrix, it's very, very tricky. Okay? So I'm never going to ask you to find the determinant of a 3 by 3 by hand, or a 4 by 4, or something up higher than that. It's so tedious that we're just going to have you use your calculator like we did in example 7b. The only one I'm going to ask you to do by hand is for a 2 by 2 matrix, which we'll talk about in example 8. Okay, determine whether the matrix has an inverse. Let's find the inverse now. So my determinant of matrix A the determinant of matrix A will be 3 times 2 minus 4 times 1. So that will give me 6 minus 4, or 2. So my inverse matrix will be 1 over the determinant, switch these 2 and 3, and make these negative. So what we're going to have, our inverse matrix will actually be 1, negative 1/2, negative 2, and 3/2. There is our inverse matrix. Now, putting this into our calculator here, we can check it. So I have 3, 2, 4, 3, 1, 4, 2. We can find the determinant just to make sure we did it correctly. Determinant matrix A. You see is 2. Now to find matrix A inverse, we'll put this in fraction form. So you can see there 1, negative 1/2, negative 2, and 3/2. So we actually did that correctly. There is your inverse of that matrix. Now if you look at example B here, this is a 3 by 3 matrix. So again, I don't want you to find that using your by hand. Let's actually put it into your calculator. This is a 3 by 3 matrix. So 1, 2, negative 1, 2, negative 1, and 3, negative 1, 0, and 1. Let's find the determinant of that matrix. Determinant of this matrix is negative 10. A has an inverse. Now to find the matrix, or the inverse of this matrix here, A inverse. So the inverse here will be negative, or 1/10, 1/5. One-tenth, 1/5, and negative 1/2. Now we'll do the rest of it, 1/2, 0, 1/2. And the rest will go 1/10, 1/5, 1/2. There is A inverse. Now we're going to list some important properties of matrices, some of which you'll be asked to prove in the exercises. Now, it does follow the commutative property. So A plus B, matrix A plus matrix B equals matrix B plus matrix A. Multiplication doesn't always hold in general, so you need to be careful. You got to understand how it's going to work. It does follow the associative property. Matrix A plus matrix B plus matrix C is equal to matrix A plus B plus C. It does also follow in multiplication that same way. Now it does have the identity property, the inverse property, the distributive property, multiplication over division, and multiplication over subtraction. It does follow that. Now here's some application. Here's one application where I work with in example 9. Points in the Cartesian coordinate plane can be represented by 1 by 2 matrices. For example, the point 2, negative 3 can be represented by the 1 by 2 matrix 2, negative 3. We can calculate the images of points acted upon by some of the transformations studied in section 1.5 using matrix multiplication as illustrated in example 9. Now this is something you actually did in geometry class or were supposed to. So this shouldn't be anything new to you. So if I have to reflect something across the x-axis, here's how it's going to work. The only thing that's really changing is your y value when reflected across the y-axis. So we're going to have xy. We're going to multiply that by 1, 0, 0, negative 1. So when we multiply this, we'll have x times 1 plus y times 0 for your first part. For the second column, you'll have x times 0 plus y times negative 1. So when we do simplify this, you'll end up with x negative y. So there's your reflection across the x-axis. The x value changed, the y value did not. So therefore, you just proved it. Now also, we can prove it across a reflection across the y-axis. Again, much the same way. We'll take our point xy. We're going to multiply it by negative 1, 0, 0, 1. So when we do that, we've got a 1 by 2 by 2 by 2, so therefore it will work. So we'll have x times negative 1 plus y times 0, and x times 0 plus y times 1. So when you simplify this, you end up with negative x, y, which does make sense when you reflect a point across the y-axis, your x value will be opposite, not your y. So therefore, you just proved how to use matrices when reflecting things across the x and y-axis. Now your homework is a little bit different. Your homework is numbers 3 through 48 multiples of 3, 62 to 67. It's a little bit different than what your paper says. Remember, you do not have to do 51, 54, 57, or 60.